Steps to find perfect Bayesian equilibrium in signaling games. This recording assumes you are familiar with Bayes' rule and familiar with the education signaling game covered in chapter 29. What are the 4 steps to find perfect Bayesian equilibrium in signaling games? Step 1, start with a strategy for player 1 without consideration for optimality. In other words, we're going to assign a strategy to player 1 and not ask at this point whether it's optimal for that player to adopt that strategy. That'll come in step number 4, the verification. Step number 2, compute the posteriors via Bayes' rule whenever possible. So here we're in the shoes of player 2, who has incomplete information as to the other player with whom he or she's playing the game. And this player 2 is reassessing the situation. That's what computing the posteriors really means. Step number 3, given this new assessment, these new posteriors, compute player 2's optimal action. All right. And now we go back to step number 1. Step number 4 says, go back to step number 1 and check whether player 1's strategy is optimal given player 2's strategy in step 3. This is like a backward induction. In other words, here we have the early player thinking ahead of how it is that player 2 will interpret player 1's actions and respond, and then predicting the welfare consequence for player 1. Okay, so player 1 is going to be thinking, if I do A, then player 2 is going to have this posterior, this assessment, and is going to respond in this way, and I'm going to get this utility. On the other hand, if I do B instead, player 2 is going to reassess the situation, is going to respond in a particular way. That's step number 3. And I, player 1, am going to get a different utility. So should I do A and get that utility, or B and then get this utility? That's going to be essentially figuring out what is optimal for player 1 to do, anticipating player 2's response. It's like a backward induction. And we'll compare that to the strategy in step 1. And if they match, then we have verified the optimality, and everybody's optimizing, everybody has rational beliefs, and we found then in that case a perfect Bayesian equilibrium. All right, these are the 4 steps. You should have them very clear in your mind, and there's nothing new here. This is already covered in slide 11 of chapter 28. Just presented slightly differently here. Now, we're going to illustrate this algorithm in the context of the education signaling game. So let's try to find all pure strategy, perfect Bayesian equilibrium. Mixed strategy, ones will be reviewed in a separate video. Let's start out with, okay, so here's the game. Nature picks player 1 to have high ability or low ability with probability 1/3, 2/3. Then that player, whatever the ability, chooses to either become educated, go to college, or not. Likewise over here. And then player 2, who's the firm and doesn't know the ability type of player 1, that's why there's the information set here, needs to choose whether to make this job applicant a manager or a clerk. That's the game. It's player 2 here who has incomplete information, and it's player 1 who has the opportunity to send out a signal as to his or her type. The payoffs I'm not going to discuss here. I assume you're familiar with them. All right, so this is the education signaling game, and we are going to now go through all possible pure strategy equilibria to try to identify them. So let's start out with the possibility that the high ability type gets educated and the low ability type does not get educated. That's step number 1. We've specified a strategy for player 1. And we don't know yet whether it's optimal. Step number 2, compute the posteriors via Bayes' rule. All right, so in any separating strategy, as you know, Bayes' rule will imply that the player is going to know the truth about the types. So if somebody's educated, player 2, who's assumed to know the strategy of player 1, though not who player 1 is going to say, well, the only people who got educated are high ability types. So my posterior, my Q, is 1. For sure, this is a highly able person. And so then the firm is going to choose what? So we're dipping into step number 3 here. The firm is going to say, well, if I think it's a highly educated person rather than this over here, I can make that person a manager and player 2 can get a 10, or I can make the job applicant a clerk and get a 4. And for me, the firm, therefore 10 is better than 4, I choose manager. All right, so we've computed the posterior upon observing an educated job applicant. And that was for sure this is somebody who's high ability type. And then given that posterior, we've computed player 2's optimal action. The firm will choose to make somebody who's educated a manager. All right, so let's write here. The Q is for sure you're highly educated. And the best response is that if educated, then make a manager. All right, now let's go back to step number 2 and 3. In the event that the firm observes that the job applicant is not educated, Bayes' rule again in a separating behavior is going to imply that the firm knows the truth. It's going to say, oh, this person's not educated. I understand that the only people who don't get educated are low ability people, so I believe that for sure this person is low ability. So the firm is going to be thinking about this node rather than this node. And then the firm, step number 3, given this posterior, is going to compute what's best for the firm. It says, well, if I make this job applicant who I think is low ability a manager, I, the firm, get a 0. If I make this job applicant a clerk, then I, the firm, get a 4. And my best response is to make the person a clerk. All right, so step number 2 here is if I observe the job applicant is not educated, then my optimal action, that's step number 3, is to make the person a clerk. All right. Now, step number 4 is to go back to step 1 and check whether player 1's strategy is optimal given the strategy in step number 3. So let's check that. We have really 2 types and both have to be optimizing. So let's say you're a high ability person. You get to choose whether to be not educated or educated. So if you're not educated, then the firm is going to think of you as being low ability. It'll be a wrong thought, but that's a red herring. The fact of the matter is that the firm is going to make you a clerk, and you, the high ability person, are going to get a payoff of 4. So that's one possibility. The other possibility is that you choose to become educated, and the firm will believe that you're a high ability person. Turns out to be correct, but that's a red herring. The fact of the matter is that you would be made a manager, and you, player 1, would get a 6. So your choices are not get educated and get a 4, or get educated and get a 6. What's best? The best thing is to get educated. So is it optimal for a high ability person to get educated? Yes, we just checked that. So correct. All right, HE. Okay. Now let's look at it from the perspective of the low ability person. Again, you can choose not to get educated or get educated, and then needs to predict how it is that this is going to be interpreted and how the firm is going to respond and what the ultimate welfare consequence is. So if the low ability person does not get educated, then we know that the firm is going to believe correctly, but again, neither here nor there, not relevant whether it's correct or not. The firm will believe that this is a low ability person, is going to make this person a clerk, and the player is going to get a 4. Excuse me, a 4, player 1. On the other hand, the low ability type can get educated and be made a manager. You get a higher salary, but it's so costly to get educated, and your payoff ends up being actually lower, 3. So for the low ability person, N leads to a payoff of 4, and E leads to a payoff of 3. What's optimal is then N. So If you're a low ability person, then not getting educated is optimal. So we've completed step number 4. What is optimal for player 1, and does it match up with the strategy assigned in step 1 without any consideration for optimality? Yes. Therefore, we have found a perfect Bayesian equilibrium, and the equilibrium is the strategy of player 1 is as in step 1. The strategy of player 2 is as in step 3. And the posteriors, which are part of the description of the equilibrium, as in step 2. And that is the full specification of that equilibrium. All right, so this was just one of the possible pure strategy equilibria. We'll go through the other 3 combinations a little more quickly here. So what about whether there might be an equilibrium in which the high ability type does not get educated and the low ability type does get educated? Is that possible? That's a question. So that's basically step number 1. We've assigned a strategy for player 1. Compute the posteriors via Bayes rule. This is separating behavior, and in separating behavior, the player 2 always deduces the truth. That's a basic implication of Bayes rule. So the posteriors here are going to be if player 2 observes no education, then it's going to be sure that this is a high ability type. And if the firm observes education, then the probability that this is a high ability person is 0, because only the low ability people get educated. So over here, the posterior Q is equal to 0. All right, step number 3, compute player 2's optimal action. Okay, so if an education is observed, then because the firm believes that for sure this is a low ability person, the firm is going to make this person a clerk. Okay, so, it's going to be thinking that it's over here. And we've seen that in that case for the firm, it's better to make that person a clerk and get a 4 for itself rather than a 0. So then clerk. On the other hand, if the firm observes that the applicant is educated, because the only people who are educated are, we're talking now about if the person is not educated. So if the person is not educated, then the firm is going to think that for sure this is a high ability person, because only the high ability people get educated, get not educated. And so the firm is going to think that it's over here, and it's going to say, well, if I make the person a manager, I get a 10. If I make it a clerk, I get a 4. Clearly what's best for me, the firm, is to make this person a manager. And so if the person is not educated, then make the job applicant a manager. Step number 4, anticipating the behavior in 3. What is best for player 1? All right, so if it's a high ability type, what happens? If you're a high ability type and you don't get educated, the firm is going to think that you are high ability and is going to make you a manager, and you get a payoff of 10. On the other hand, if you become educated, which is the type of thing that the low ability person does in the separating candidate equilibrium, then the firm is going to wrongly interpret you as being low ability person, is going to make a clerk, and you get a payoff of 0. So clearly it's best for you, the high ability person, to not get educated. All right, so the high ability person wants to not get educated. What about the low ability person? The low ability person can get educated, and the firm would then believe that you are a low ability person and make you a clerk, and you get a payoff of -3. Or you can become not educated, and this is the type of thing that a high ability person does, and that's going to lead the firm to wrongly believe that you are high ability person, and it's going to make you a manager, and you get a PF of 10. So between not getting educated and getting a 10, or getting educated and being made a clerk and getting a -3, clearly not getting educated is better. So for the low ability person, a not education is best. In other words, it's better to imitate the behavior, the way of being of a type that you're not. And so the answer is no to step 4. The strategies specified in step 1 are not optimal, in particular not optimal for the low ability person. The low ability person wouldn't, it's not true that it would want to be want to get educated or want to not get educated. All right, so there is no separating equilibrium in which a high ability person gets not educated and a low ability person does. All right, so let's now turn to pooling equilibria. Is it possible to have an equilibrium in which both types, high and low ability, get educated? All right, so let's say both get educated and the firm observes that the job applicant is educated. Well, according to Bayes' rule, the posterior is the same as the prior in this case. And the prior here is 1/3. Okay. So when you observe something that you expect to observe, then the posterior is the same as the prior. All right, so what would be the optimal response of the firm? Let's compute that over here, and we'll deal with the other posterior in a moment. The firm can say, well, let's see, the utility of the firm of making the job applicant a manager is that the firm would get, with probability 1/3, the firm would get a 10, so 10 times 1/3. Then again, there's a probability 2/3 that the firm, that the person is low ability, and the firm gets a 0. So plus 0 times probability 2/3, and that expected value then is going to be 10/3. Okay, so that's the expected utility of making the job applicant a manager if you observe that he or she is educated. On the other hand, what's the expected utility to the firm of making that job applicant a clerk? Let's figure that out. U of C, so the firm gets 4 either way. Okay, and so the expected value there is 4. Which one is best? Well, you make the job applicant a manager, you get 10/3, and you make that applicant a clerk, and you get 4. Clearly, 4 is better. So the optimal response is the following. If you observe education, then make the person a clerk. Okay. All right. Now let's consider the other response. So let's say that the firm observes the job applicant is not educated. So the firm is in this information set over here. This is something completely unexpected because in this candidate equilibrium, every type gets educated. And so this is one of those completely unexpected things. Bayes' rule does not apply, and the belief is unrestricted. So if N, then the posterior P is unrestricted. Okay. Very good. So what is the best response if the firm observes the person is not educated? It could be either M or C, depending on the unrestricted prior posterior P. All right, now we're going to verify that the strategy specified in step 1 is optimal. And we're going to exploit the fact that in step 3, one of the posteriors is unrestricted we're trying to support a positive answer for step 4. All right, so let's take a look here from the perspective of the, let's say, not educated person or the low ability person. The low ability person can say, if I get educated, then I would, the firm would make me a clerk. Likewise, if you're a high ability person, you got educated, you made a clerk. And so the payoff to the low ability person would be a -3. If you don't get educated, then depending on what the posterior is, you get a 0 or a 4, and both are better than -3. So for this to be an equilibrium, and in particular for it to be optimal for the low ability player to get educated, we gotta make sure that, well, essentially there's nothing that can be done, right? So it doesn't matter what the posterior is. The firm is either going to make this person a manager or a clerk, and in either case, the payoff there is better than the one of getting educated. So the answer to step 4 is no. Whatever P, E is not optimal for the low ability type. That makes sense. Why would you, as a low ability person, go through the trouble of getting an education, which is very difficult for you, if you're going to end up as a clerk anyway? The worst that can happen if you don't get educated is you made a clerk. And in that case, you save yourself the trouble of education. So really, there's no point. All right, so no, the answer is there is no pooling equilibrium in which both get educated. And now to the last equilibrium, or candidate equilibrium. Is there one in which both types of player 1, high and low ability, get not educated? All right, so that's step number 1. We've specified a strategy for player 1. Let's compute the posteriors. The posteriors are the following. If you observe n, well, that's what you expect. The posterior is the same as the prior. And that is to say that P is equal to 1/3. Let's then figure out what is the best response of the firm. Well, with probability 1/3, you get a 10. With probability 2/3, you get a 0. The expected value of that is 10/3. If you choose C to make the job applicant a clerk, then you get 4 either way. And so 4 is bigger than 10/3, and therefore the optimal response of the firm is, if you observe no education, is to make the person a clerk. All right, now let's consider the other possibility, that the firm observes that the job applicant is educated. In this candidate equilibrium here, this is something that nobody ever does. Everybody chooses not to get educated. So you're stumped here, and there is no restriction here. So if E, then the posterior Q is unrestricted. And we're going to exploit that flexibility here towards supporting a positive answer in step 4. All right, so in step 3, given this unrestricted posterior, what is player 2's optimal action? Well, it depends. If E could be either, depending on Q. If Q is high enough, then it'll be optimal to make the person a manager. If Q is low enough, vice versa. All right, so now in step number 4, let's check that it's optimal for both types to not get educated. Let's take a look here from the perspective of the high ability player. If the high ability player does not get educated, in step number 3, we've already concluded that the firm would want to make this job applicant a clerk, and so the high ability person would anticipate a payoff of 4. If the high ability person were to choose to get educated, then in step number 3, we said the belief is unrestricted, and it could be that the firm makes this person a manager or a clerk. We cannot allow for a manager because then the high ability player would get a 6, which would be better than a 4, and the answer then would be no. That wouldn't be optimal to play N for the high ability player. And so we want to make sure that the firm then chooses C. that would make it optimal for the high ability player to choose N. And I would say, oh, I made a clerk, I get a 4. If I get educated and I made a clerk, I get a 0. Clearly, then in that case, high ability player would choose N. So we need that. We need the firm to be led to choose C, and that in turn is going to require a low enough posterior Q. So let's keep that in mind. We're going to compute that Q in a moment. But from the standpoint now of the low ability person, is it optimal to not get educated? Well, if you do not get educated, remember the posterior is the same as the prior, and as we computed in step number 3, that means that the firm is going to make this person a clerk, and the low ability person then anticipates a payoff of 4. If you're made educated, if you become educated, then it really doesn't matter whether the firm would make you a manager or a clerk, because the payoff would be worse. It would be either 3 or -3. They're both worse than 4. So there's no question here. It doesn't really matter what the firm would do here. It is optimal for the low ability player to not get educated. So the only thing that's left hanging here is the optimality of player 1 needs to be guaranteed by making sure that upon a choice of E, that the firm would then choose C. And so for that, what we need is the following. What's the expected utility of making the person a manager? Well, if you make the person a manager from the firm's perspective with probability Q, this is a high ability person and the firm gets a 10, so 10Q. And with probability 1 minus Q, the firm, this would be a low ability person, and making that a manager, the firm gets a 0, and so the expected value of that is just 10Q. On the other hand, the expected utility to the firm of making a job applicant a clerk is what? Is 4 either way. And so as we discussed, we need to make sure that a clerk is best, and so we're going to make sure that 4 is better than 10Q. Which is to say that Q has to be less than 0.4. Okay, all right, so the posterior needs to be pessimistic enough. The firm needs to say, oh my gosh, I just observed something totally unexpected. I don't know what to think of it. Well, the thinking has to be pessimistic, has to be cynical. You know what? These people who get educated are most likely just trying to fool me. Most likely this job applicant is low ability. Okay, that Q has to be at most 0.4. Then it is indeed optimal for the firm to choose to make that person a clerk, and therefore for the high ability person, closing the loop, it would then indeed be optimal not to get educated, anticipate being made a clerk and getting a 4, rather than getting educated and still be made a clerk but get a 0. So the answer here is yes, and therefore the equilibrium here is that the strategy of player 1 is, as in step 1, not get educated, whatever the type. The strategy of player 2 is as in step 3, that is make the person a manager if, excuse me, that is to say make job applicant clerk, whatever educational status. And what are the beliefs, the posteriors? P is equal to 1/3, okay? And the Q is anything less than 0.4. All right, so hopefully this has been a helpful, if perhaps somewhat long, illustration of this algorithm of how to compute perfect Bayesian equilibria in signaling games. Step number 1, assign a strategy to player 1 without worrying about whether it's optimal. Step number 2, compute the posteriors of player 2, and they will be influenced by that strategy of player 1. Then, given those posteriors, compute player 2's optimal action. And step number 4 is a backward induction. Put yourself in the shoes of player 1. Anticipate how it is that, depending on the action taken, player 2 is going to respond via the posteriors that get updated in player 2's mind, and check whether the strategy that you're supposed to be following, step number 1, is actually optimal. If it is, then you've closed the loop and everybody's optimizing and all the beliefs are rational and you have a perfect Bayesian equilibrium. And that is extremely important that you have these 4 steps very clear in your mind as you attack a problem. In a separate video, we will analyze this game to look for mixed strategy, perfect Bayesian equilibrium.